Right, so good morning, everyone. So let's start today's session. So previously, in previous sessions, we discussed both about gravitational field, how they behave, and electrostatic field as well, right? So the last field, right, last type of field that we are going to study and analyze is uh, so-called magnetic field, right? Magnetic field. I hope you have heard about this magnetic field, right? Uh, because in waves we learned about electromagnetic waves, right? Electromagnetic wave. There was electromagnetic waves were governed by this electric and magnetic field. Right? We have already learned about the electric fields, and here it is magnetic field. Right. So first, the introduction, right? So the magnetic field was actually this is very old. Many years ago. So, for example, for a typical example of this magnetic field, utilization of the magnetic field is the compass, right? Compass, right? Compass needle, right? So we know what is compass is, right? Normally, it is used to. So there's a uh, compass. Typically, it is a circular shaped one, circular shaped one, and there is a needle here. There is a needle here, and it is noted north, south, west, east in that manner, and always this compass, right? Always this compass, this is pointed, right? This is pointed towards the north, right? No matter the direction that we are oriented, right? Say we are we are directed towards south, but the compass automatically, this arrow, the compass needle would be rotated to this north side, right? So that is due to this magnetic field, so-called magnetic field. Actually, this was first found by Chinese people, this compass. That is due to this magnetic field around, right, around the Earth. The magnetic field around the Earth. Right, so this is Earth. Right, so there's a magnetic field around the Earth like this. Start from north. Start from north and goes towards south. Right? Goes towards south. There's a magnetic field like this. Right, so in this section, we will learn about different types of magnets. Like there are bar magnets, horseshoe magnets, and uh, the magnetic field induced in a conductor, so the coil. Right, so different types of magnetic field we will study here, as well as we'll try to get some expressions for each as well, right? And we'll learn some laws related to that. Like for example, called Biot-Savart law, and like right, and maybe yeah. So those kind of laws, and so here first we'll see the most basic one, right? So the the force acting on a current conducting by placed in the magnetic field. So basically, there are two types of magnetic fields, right? Right? Two types of magnets, actually, not magnetic field. Two types of magnets. One is called two types of magnet. One is called well, there are two types: permanent magnets and induced magnet. Right? Two types of magnet. two types of magnets. There are two types of magnets. First one is called uh, two types of magnets. First one is called uh, the permanent magnet. Right, permanent magnets. Right, so permanent magnets are basically the magnets which can be found naturally, right? Naturally. For examples like bar magnet, shoe magnet, yeah, are made of normally the ferrous and nickel. That consists of ferrous or nickel as the substance. And second one is induced magnet. Right? Induced magnets. Induced magnets. So as the name says, they are not permanent, induced. Right? So its magnetic properties of that induced magnet are temporary. And temporarily just would be able to observe, right? This in induced magnets, this magnetic properties would be able to observe only if the current flows through the through that element. Right? There is some element, right? A conductor. Right? If you consider conductor, if current flows through a conductor, right? If current flows through a conductor, right? If current flows through a conductor, then that conductor would become an induced magnet. Right? Right. So, for example, is a current carrying conductor. Can be considered as an induced magnet. Current carrying conductor. Right. So, if suddenly current flow is stopped, whatever, the magnetic properties of that conductor also be lost. Right. So, only if the current flows through the conductor, this magnetic properties would be there. So that's why they call as induced magnet. But whereas we consider some uh, magnets like shoe magnets or bar magnets, which are made of iron or nickel. So the current flow is not necessary actually. Internally, there happens the magnetic properties are internal to that. Right? Magnetic property is internal to those permanent magnets. Right. Right. Uh, right. So then we will talk about the force acting on a current conductor via phase in a magnetic field. Right. So for that, let's consider a shoe magnet. And a shoe magnet. So this is just an experiment. So horseshoe magnet actually. Right. Consider horse magnet and a conductor placed in between this horseshoe magnet. In between this horseshoe magnet, right? In between this horseshoe magnet, right? So the current carrying horseshoe magnet, as an energy, it is kind of the shape is something similar to a horseshoe, right? Like this horseshoe, kind of similar to this, and the one side is called north, and the other side is called south. And this there would be a magnetic field from north to south, as we discussed on the Earth magnetic field. Or Earth also have some magnetic field around itself from north to south. So always magnetic field is from north to south. And always magnetic field is north to south. And if a conductor is placed like this, just a conductor. Right? So initially nothing would happen. Here nothing would happen. This conductor is a conductor would be there as it is. Right? Nothing would happen. Nothing special would happen. Right? Nothing special would happen, but right, so here nothing special would happen. Right? So just place the conductor. So nothing would happen. No special thing would happen. Right? So experimentally it was found nothing special happened here. Right? So just the conductor would be there as it is. But if a current is flowed, right? If a current is flowed, right? If a current is flowed like this, that's if a current is flowed through this conductor by an external, let's say a battery is connected to these two terminals of the conductor, then current would flow in this manner. And current would flow in this manner, and it was found now it is this conductor would move now. Let's say upward. So later we'll discuss why this is moved upward, not downward or anywhere, any in any other direction. So let's for now let's say this move upward due to some force, right? The force is applied in upward direction. So suddenly this conductor will be moved upward. So basically, when current is allowed to flow, allowed to flow, allowed to flow through the conductor. Right? When current is allowed to flow through the conductor is subjected to force. So conductor would throw away. Above conductor is found to be thrown away, right? Thrown away, right? Thrown away. So why is that? Right? Thrown away. So because that is due to a force, right? I mean, initially the conductor, when the conductor is just kept without applying any current through that conductor, it would just stay as it is, right? Without any special a special effect. But when suddenly if current is let current is allowed to flow through the conductor, it is now just uh, right, it is thrown away or moved. Here it is up, right? It is in the upward direction. So why? Because in order to move something, right? In order to start the motion of some object from the mechanics, we know force should be applied, right? So the final conclusion is here a force should be induce, or force should be applied on this conductor. The final conclusion is when a current carrying conductor, final conclusion is right. So the conclusion from the above experiment, that when a current carrying conductor, and it is not just a conductor, current carrying conductor, right? Current carrying conductor, right? When a current carrying conductor is kept, the current carrying conductor is kept in a magnetic field, a force would be, so that is called as magnetic force. A magnetic force is induced, right? Magnetic force is induced. A magnetic force is induced. Magnetic force is induced on the conductor. So that's the observation here, right? When a current carrying conductor, right? When a current carrying conductor, not just a conductor, if a conductor is just placed on in the magnetic field, nothing would happen. But a current carrying conductor is kept in a magnetic field. A magnetic force is induced on the conductor such that it would be thrown away, right? So it would be thrown away. Right? So it would be thrown away. Right? So let's now we'll try to find an expression for that. Right now we know what happens here. Force when a current carrying conductor is kept. Right? When a current carrying conductor is kept in a magnetic field, there would occur a force. Now let's try to quantify it. Right? So for that, consider a current carrying conductor length L, right? Length L, at length delta, let's say delta L, length delta L, and current I, kept theta degrees angle, theta degrees angle, degrees incline. And so to get a general expression, let's keep it theta degrees incline to a uniform magnetic field. Right, so uniform magnetic field, right? Uniform magnetic field. I'll denote it by just magnetic field. Magnetic field. Let's say B. That's a magnetic field, right? So there is a uniform magnetic field now flowing towards right. Some uniform magnetic field flowing towards right. And a current carrying conductor of length delta L and amount of current I, right, is kept at an angle of theta degrees to the magnetic field. So this is the direction of magnetic field. It is flowing towards right. Magnetic field, and it is flowing towards right. So experimentally it was found. It was found that magnetic so it was found that the magnetic force, it was found that the magnetic force, right, the magnetic force, it was found that the magnetic force F, say F, acting on the conductor right, is proportional to obviously to the current. Proportional to the current. If the current, the amount of current flowing through the conductor is higher, the magnetic, the strength of the magnetic force would be higher, as well as the length, or delta L. If the conductor is lengthier, the amount of magnetic force applied on the conductor would be also higher. And as well as third one is this sine value, right? Sine value of the angle. Sine value of the angle between the conductors. Theta is the angle between the conductor and the magnetic field. Angle between the conductor and magnetic field, and the sine value of that. And so when these three are combined, here F is proportional to I delta L sine theta. That's sine theta. Sine theta. So in order to get rid of this proportionality side, right? So in order to get rid of the proportionality side, a constant is applied, and constant is defined, called the magnetic flux density. A constant is defined as magnetic flux density. Flux density, which is normally noted in B. So now we have F is equal B, right? So a constant, when after substituting the constant, we can put the equal sign. F is equal B I delta L sine theta. Right? Pi delta sine theta. Yes, so this is the final general expression for the magnetic force. Right? So this is the final general expression for the magnetic force. F is equal Vi delta L sine theta. So F is the magnetic force. Magnetic force. B is the magnetic flux density. I is the current through the conductor. And delta L is the length of the conductor. Length of the conductor. Theta is the angle between the conductor and magnetic field. Okay. Magnetic field. Right. So this is general expression. So if we get scenario like this, and if we get a scenario like this, if the conductor is perpendicular to the magnetic field, perpendicular and if the conductor is perpendicular to the magnetic field, if the conductor is perpendicular to the magnetic field, let's say current is I, perpendicular. Now the sine theta value, let's say is L. Length is L. Length is L. Now theta is 90 degrees, hence sine 91. And delta L is equal L. So we can modify the above expression. F is equal B by L. So B is equal F divided by IL into L. Right? Is equal B is equal F divided by IL. Right. Right. So this I into L term is defined as magnetic current element. I into L term is defined as named as current element. Current element. So magnetic flux density. So let's go for a definition. Now we know this is the magnetic flux density B. Now let's we can define that magnetic flux density. It is the force, right? According to this above expression, magnetic flux density is the force acting on a unit current element. Unit current element of a conductor kept perpendicular to the magnetic field. The magnetic flux density B, the magnetic flux density B is defined magnetic flux density B is defined as magnetic force and as magnetic force acting on a on unit element on unit current element on unit current element kept perpendicular to perpendicular to the magnetic field. Kept perpendicular to the magnetic field. So we can define the units of B of force is Newton divided by current is ampere meter. Right? Current of ampere into meter. This is special unit called T. Right? It is defined as Tesla. Right? That famous scientist Nikola Tesla. So this unit for B is defined as Tesla. The special unit for magnetic field, magnetic flux density, T, Tesla. Right. So this is the general expression that you have to keep in mind. F is equal BI delta L sine theta. So the special case is when the so what is the angle corresponding to the maximum magnetic field, magnetic force? It is when the sine theta becomes 1, whereas theta becomes 90 degrees. And so the maximum magnetic force is induced when the conductor and the magnetic field is perpendicular to each other. And here the maximum magnetic field, magnetic force. Force, right? V when theta is equal 90 degrees. That is force when the conductor and magnetic field conductor and when the conductor and magnetic field when the conductor and the magnetic field is perpendicular to each. Conductor and magnetic field is perpendicular to each, right? Each other. Right. Uh, then we'll talk about some of the basic magnetic various distribution of magnetic fields, right? So distribution of magnetic fields around some standard magnets, right? Standard magnets. Distribution of magnetic field lines, right? Magnetic field lines on some standard magnets, on some standard magnets, right? So first one is, let's consider a bar magnet. A bar magnet. A magnet like this. Right? So one half of the bar magnet you have seen has marked in typically it is in blue and marked as N. The other half is in red and marked as S. The magnetic field around the bar magnet is from north to south, like this. From north to south. Like this. Then a shoe magnet. Second one, a horseshoe magnet. Across a horseshoe magnet, the magnetic field would be like this. Right, so this is south pole, this north pole. Magnetic field distribution would be like this. So north to south. From north to right. So this is the horseshoe magnet. And so here from these two figures, you can see uh, not unlike the electric field, right? Unlike the electric field. So for electric field, so because it's a positive charge like this, the electric field around the positive charge, we can draw in this manner. But here, the specialty here is there cannot be just a north pole or just a south pole. Separately, right? Separately, there cannot be a north pole and south pole. Always in a magnetic field, both north pole and south pole should be present, right? Both north pole and south pole should be present on the same magnet, right? Unlike this electric field, right? If it is just a positive electric field, positive charge, electric field would be induced around it. We don't know whether, uh, right? We don't know where is the negative negative charge. Negative charge will be somewhere infinite, doesn't matter. But here, close in a magnetic field, the specialty is always the north pole and south pole are uh, close together. Right? They are on the same magnet. Right? So there can be just uh, north pole separately and south pole separately. And the special point is, unlike electric field, right? Unlike electric field, uh, one type of element or one type of fault. Here they are called fault, right? North pole, south pole. In this north pole, this is south pole. Like electric field, here in magnetic field, magnetic field, both north pole and south pole should be present. Both south pole and north pole should be present on the same magnet. On the same magnet. For example, let's say we have a bar magnet like this. At north, north, south. Right. So if this is just broken here, just at the symmetrical axis. And so would the left side be North Pole and just would the right side be South Pole? No, right? No. The left side, and so left side would be again, it would be a magnet, both consisting of North Pole and South Pole. And again, it would be a magnet. Right? So divided here. And the resulting would be two magnets, not just a North Pole separately and South Pole separately. There would be two magnets having North Pole and South Pole on both of the magnets. Like this. So the result is two bar magnets having North and South Pole, not just North Pole separately and South Pole separately, right? So if this bar magnet is just divided on the symmetrical axis, it won't result a North Pole separately and a South Pole separately. It would result two small bar magnets having both North Pole and South Pole on each, right? That you have to remember. And another thing about this permanent magnet, when they are heated, the magnetic properties will be lost. That's some additional information. If permanent magnets are heated, magnetic properties may lose. So magnetic properties may be lost and may lose. So another point parameter. So normally the magnets are not heated. Right. So these are two types of permanent that I show. And the other type of magnet is the induced magnet, right? Induced magnet. So induced magnets and induced magnets. So I will talk about three types of induced magnets. Right. So to find this direction of magnetic field, here it is easy. Right. Here it is easy. For a permanent magnet is from North Pole to South Pole. Right. For a permanent magnet is easy. Right. So normally, so always it is from north to south. Right. For a permanent magnet, magnetic field direction is from North Pole to South Pole. Direction of magnetic field lines or flux lines. Direction of magnetic flux lines is from North Pole to South Pole, from North Pole to South Pole. But for induced magnet, how to find the direction? Right. So for induced magnets, to find the direction of the magnetic field, in induced magnet, right hand screw rule should be used. That we have already discussed earlier as well. And on a couple of circumstances, like in mechanics fields, in mechanics, to find the direction of movement, we use the right hand screw rule, right? Right hand screw rule. Same thing can be applied here. Right, to find the direction of magnetic field right hand screw rule can be used. So what is right hand screw of screw rule? And so we have to grab the four fingers, just so grab the four fingers and point the thumb outward. Right? You grip the four fingers and point the thumb outward. Then we have to direct our. So we can direct right. So there are a couple of occasions like this. Right? So here, let's consider these two cases. First one, there could be a current carrying conductor just outward. Right? So you know this notation. A dot represent current carrying conductor where the current is flowing. Current carrying conductor perpendicular to the whiteboard. Here, the current carrying conductor perpendicular to the whiteboard. Conductor perpendicular to whiteboard. At current carrying conductor perpendicular whiteboard. So this is the direction. Right now here current is flowing outward from the whiteboard. So this represented, so it is a dot, it is a cross like this. Then it represents current is flowing into the whiteboard. It is dot, current is flowing out from the outward from the whiteboard. Second case is when there is a loop, circular shaped current carrying conductor. Circular current carrying conductor. If it is circular current carrying conductor, like this, circular current carrying conductor, circular. Current carrying conductor is circular. Let's say current is flowing this direction. Right? Current is carrying flowing in this direction. Then to find the magnetic field, so there would be two magnetic fields. There would be a magnetic field induced on both of these occasions. The current carrying conductor is perpendicular to the whiteboard, and there's a circular current carrying conductor. So to find the direction, that's what we have to do is we can use the right hand screw rule. So here in the first case, you have to point your thumb towards the direction of current. Right? You have to point your thumb towards the direction of current. which is outward from the whiteboard. Then the other four fingers would represent the direction of magnetic field. Right? So when you point your thumb in the direction of current, which is outward from the whiteboard, right? It is outward from the whiteboard, right? It is outward from the whiteboard. The four fingers would be directed. The four fingers would be directed. The four fingers would be directed towards right, right? Like this. Sorry about the drawing, it's not good. Right, so this is the direction of current, and this is the direction of the magnetic field in this case. So direction of magnetic field is anti-clockwise. I use another different color. Anti-clockwise. Right. So in this case, we have to point our four fingers in direction. So we cannot find our thumb in the direction of current because it's not a straight conductor. So now we have to point our four fingers in the direction of in the direction of the direction of right, in the direction of rotation, the direction of current flow. So here thumb would be pointed. Right? So here this is the direction of current. So thumb would be pointed toward the direction of the magnetic field. So interchangeably you can use it. Accordingly, we have to consider. So here in the first case, he pointed the thumb towards the direction of current, and the other four fingers are then directed towards the magnetic field. In the second case, we have to point our four fingers in direction of current because it is we have to point our thumb the direction of the current because is the direction changes. The current carrying circular current carrying conductor. Therefore, the magnetic field is towards left, towards right. So there will be a magnetic field like this. So there would be a magnetic field like this around this. Around the circular shape conductor, right? So we have to use right hand uh, screw rule to obtain that. Right. Then we'll see. Actually, we discussed here. We discussed that when to right. So when a conductor is kept, concurrent conductor is kept in a magnetic field, a force would be induced. Actually, now since we know the field representation around some standard current carrying conductor, we can. So there's another one. So let's consider the third one as a coil, right? Magnetic field around a coil, inside a coil, or inductor. Magnetic field around the solenoid. Solenoid around the solenoid carrying current. So let's consider solenoid like this. So current is flowing in this direction. So here also we have to point our forefinger in the direction of currents. Same as here, same. So same, we get same direction as is. Right. So here also current, the magnetic field is in this manner. Right. Right. So now let's see actually how this force is induced, right? Force is induced in between two magnetic field. Yeah. Right. So consider case where a current carrying conductor is brought into a uniform magnetic field. Magnetic field like this. So let's say we have current carrying conductor which is like this. So current is flowing outward. So the magnetic field around it anti-clockwise manner. Clockwise manner, and there is another horseshoe magnet. So we have a horseshoe magnet like this. North pole, right? So I will just draw the two terminals of the horseshoe magnet, not the other part. That's a north from north pole to south pole. So play with your north to south. The magnetic field would be from north to south. From north to south. So when this conductor is brought into this magnetic field, permanent magnetic field, so what would we have? So what would be the resultant magnetic field? Conductor is brought here, right? So you can see the towards left side from this conductor, both magnetic field induced by the permanent magnet, right? The magnetic field induced by the permanent magnet is towards downward, and the magnetic field induced by the conducting wire is also towards downward. So we would have a resultant magnetic field, a strong resultant magnetic field towards down. But whereas we consider the right side, the permanent magnet would induce the magnetic field is downward due to the permanent magnet, but the induced magnetic field would be magnetic field around the conducting wire would be downward. So they are opposite direction. So here we would have somewhat a weaker magnetic field. Weaker magnetic fields towards right. So therefore, so here the magnetic field is stronger. Here, magnetic field is weaker. Right? Strong magnetic field. Here, somewhat weaker magnetic field. So the result would be, sorry, so what would happen? If the magnetic field is stronger here towards the left, the magnetic field is stronger than the right side. There would be a force acting towards the weaker side from the stronger side. Right? So this conductor would be force towards right. Right. So this is how the conductor would be shifted to the right. Right. So here conclusion is left side to the conductor, magnetic fields are added up resulting a strong magnetic field. Whereas right side to the conductor, whatever, right side to the conductor, whereas right side to the conductor, the magnetic fields are cancelled out. Right? Cancelled out, resulting a weaker magnetic field. Resulting a weaker magnetic field. Therefore, the conductor would be shifted towards right. So due to this variation in magnetic field, the conductor is shifted towards right. And the conductor is shifted towards right. The conductor is shifted towards right. So that's how this force is applied on the conductor. Right? But it is somewhat complex. I mean, not complex. That's a tedious process to consider the magnetic field and right, so draw the magnetic field and find how the magnetic field variation occurs around the conductor and coming to the result of the direction of force is somewhat not convenient, right? So it is a time-wasting process. So therefore, a scientist called Fleming. Right? Fleming has come up with an easy method, actually, easy method to find this force, direction of force, if the current, the direction of current and the direction of magnetic fields are known, right? So we can easily find the direction of force like above without drawing this magnetic field and all those things, right? Without considering these directions and all those things. There's an easy method to find the direction of force. Right? Direction of force applied on a current carrying conductor kept on a magnetic field. So that's from the Fleming's right hand rule. So Fleming's left hand rule. So right hand rule. Later we will consider there's another rule called Fleming's right hand rule as well. Later we'll consider that. Learn about that. Now it is Fleming's left hand. Right. To find the direction of the force. To find the direction of force. To find the direction of force applied. To find the direction of force applied. The direction of force still red actually. Use on a current carrying conductor. Conductor kept in a magnetic field. Kept in a magnetic field. Fleming's right hand rule would be used. On the Fleming left hand. Fleming left hand rule is used, right? Rule is used. First, you have to. So what you have to do? First, get the. Only use the. We have to only use 3 fingers here. Out of 5 fingers on the left hand, we have to use only 3 fingers. The thumb, forefinger, and middle finger. Right. So you can other 2 fingers. Right. So other 2 fingers, we don't have to use the other 2 fingers. So you can just curl them up, right? Then use the three fingers. Right. So point the 3 fingers. Right? Point this middle finger, forefinger, and the thumb such that they are perpendicular to each other. So you can point the 3 fingers in a way they are perpendicular to each other. Right? So perpendicular to each other, you have to point the other 3 fingers. All these 3 fingers should be perpendicular to each other. Right? Like this. And so you can keep the other two fingers like this. Curled up. Yeah, and we have this orientation. Right? So you have to first you have to point your thumb, forefinger, and middle finger like this, perpendicular to each other. Then this thumb will represent the direction of force. Direction of force. So this should be directed towards the direction of magnetic field. Force, let's say, and the middle finger should be directed towards the direction of current. I. So FBI, right? Force, magnetic field, current, FBI. Right? So you have to get your thumb, forefinger, and the middle finger and make them perpendicular to each other, and uh, point the forefinger in the direction of magnetic field and the middle finger in the direction of the current. Then the thumb will use the direction of the force. Right? So you can try this. Yeah, magnetic field is towards downward and the current is outward. Right? Current is outward from the whiteboard. Then the force plug in the conductor. You can use the framing instruments and find whether it is correct or wrong. Right? So the forefinger is downward. You have point the forefinger downward and the middle finger such that it is coming out from the whiteboard. Then you have the thumb towards right. Right? It's correct. So you can use the Flemish right hand. So we write the definition. When then middle finger, forefinger, and thumb and thumb are positioned in middle finger, forefinger, and thumb are positioned perpendicular to each other. Each other. Each other. Then the middle finger should be each other. Then point the middle finger towards the direction of current. Current I and forefinger towards the direction of magnetic field. forefinger, what direction of magnetic field. And then eventually the thumb will be directed the thumb will be directed towards the horse. Directed towards the force. Will be directed towards the force. Right. Right. Directed towards force. This is the Fleming left hand rule. Right. So you can easily remember this as FBI. Right. So force represent F, magnetic field represent V, current represent I. And the middle finger represents the direction of current. Magnetic field is represented by the forefinger, and thumb is represented. Thumb represents the force, direction of force. Right. So now we know. So this equation to find the force, magnetic force acting on a conductor. Right? The conductor acting wire. But we can easily manipulate this equation, change this equation, get an expression for, right? Get an expression for the force acting on an electric charge moving in a magnetic field. Force on the electric charge moving in a magnetic field. Force acting on an electric charge moving in a magnetic field. So let's consider a charge. Right? A charge. Right? So if charge is moving, like some amount of some charge is moving in magnetic field somewhere, current will be there, right? Flow of charge is the current. Flow of electron is the current, actually, right? So therefore, when a charge at velocity v, right? Velocity v, uniform velocity v, actually, at uniform velocity v, uniform velocity v for t amount of time, But the amount of time then covered L can be found. L is equal E into T. Yeah. V is equal V into T. L is equal V into T. Then the resulting current we can find. Amount of charge is Q, the resulting current I. Current I by the movement of the above charge. Above charge we can easily find by using I is equal Q over T. Is equal Q over T. Right? I is equal Q over T. Right. Right. So let's consider. Right. So consider same as before. Consider the charge Q moves with the velocity v in a magnetic field of B, theta angle to the magnetic field. Theta, direction of the magnetic field and direction of the conductor is theta. Let's say magnetic field is to the right. Charge, Q charge towards here, theta angle towards that. And we know for a conductor is for a conductor, wire the force is equal VIL sin theta. Now, by substituting these two expressions, 1 and 2, get F is equal so V is there, electric field intensity. I is equal or T, L is equal V into T sin theta. T get cancelled out. B Q V sin theta. Force acting on a this is a force acting on a charge traveling at velocity v. Theta anchored to the magnetic field. Right. So here the F is the magnetic force. V is the magnetic field density, which is Tesla. Magnetic flux density. Q is the amount of charge. V is the velocity of the charge. And theta is the angle between the velocity and the magnetic. So here also we can, so this is to just find the force in the equation, find the magnetic field magnetic force, magnetic force, the magnitude of the magnetic force, but to find direction and to find the direction, Lenz's rules can be used as well. To find the direction of magnetic force and to find the direction of magnetic force, that means that Fleming's left hand rule could be used. That Fleming's left hand rule could be used. Right. So here, when the direction and the magnetic field is perpendicular, when direction of the charge and magnetic field is perpendicular, the maximum magnetic force is induced. And the maximum magnetic force is induced is FB, which theta is equal 90 degrees, sine 90 is equal 1, is equal B QV. Now let us consider charge of Q, positive Q. Consider a charge of positive Q moving with velocity constant velocity v in a magnetic field. Magnetic field of magnetic field of magnetic flux density V. So I will denote, there's a, let's say, magnetic field flowing into the whiteboard. And this is a charge. Velocity is V initially, positive Q. And from the right hand screw rule, sorry, right hand screw, from the left hand rule, you point your forefinger towards the direction of the direction of magnetic field and middle finger towards the direction of current, which is towards right. Is towards right, direction of current is towards right, and direction of the magnetic field is into the whiteboard. Then the thumb would be pointed upward. So the force would be induced here. And force would be induced here, right, towards upward. So we do result. Charge deviate like this. So when it comes here, but the velocity doesn't change because velocity and the force are perpendicular to each other. So velocity would be same here as well. V. Now here also a force would be applied perpendicular to the velocity. So continuously now this is changing. That's continuously this is changing. So final result would be a circular path. Right? So this should take a circular path like this. Circular path. Of some radius r. So due to the magnetic field, due to the magnetic force and due to the magnetic force, the magnetic force due to the magnetic force acting due to the magnetic force acting due to the magnetic force acting perpendicular to the velocity due to the magnetic force acting perpendicular to velocity, circular motion, circular path, charge would have a circular path. Have a circular path as shown in the figure. It's always this magnetic force would be perpendicular to the velocity. So we know there is a force perpendicular to the velocity. So that is a central force. We can consider that as central force. So the resulting would be a circular path as shown in the figure, right? So let's try this example. We decide a wire of PQ of length 0.15 meter and mass 0.015 kilogram is free to slide on two smooth vertical wire as shown in the diagram. If a magnetic field of flux density 1 tesla is applied into the paper, the paper is a magnetic field, magnetic flux density to the paper, the current I required to keep the PQ in equilibrium. Right, so now the current through the PQ wire would be towards right. And we know the weight acts downward like this mg, mg, and the direction, so the magnetic field is into the whiteboard. So what would be the direction of the magnetic force induced on this current carrying conductor? You can use the left hand rule. You can use left hand rule, point the forefinger in the direction of the magnetic field and the middle finger in the direction of current. And force be given by thumb. It is upward magnetic field. Let's say Fm is the magnetic field, force field. And so in order to be in equilibrium, what is the condition? Fm should be equal to mg. In order to equilibrium, Fm minus mg should be 0. Fm equal to mg, right? So if we can find, mp is equal VIL. Fm is equal to VIL, right? And since the magnetic field and the direction of current is perpendicular, you don't have to worry about sine theta value. This one, VIL is equal to mg. And so I is asked mg over 0.015 m by 1 into length is 0.15. 0.15. So we get 1 ampere. Yes, 1 ampere is the answer. Required current is 1 ampere. Right, so here is this said uniform magnetic field is directed vertically into the paper as shown in the figure at point O. The electrons are projected horizontally with same speed but in the opposite direction. Subsequent paths of the electrons are best represented by. And so electric field is into the whiteboard. To the whiteboard. So electron is projected right. The one is also towards left. Right. So if the electron is towards right, the current is in the opposite direction. Here the current is in the opposite direction. Then apply the Fleming's right left hand rule. Right. So magnetic field. That magnetic field is into the whiteboard. Current is, so if I consider the right, the electron which is moving towards right, so current is towards left. Force is acting downward. Force. In the other, if I consider the other electron which is traveling towards left, current is towards right. Point the middle finger towards right. Forefinger into the whiteboard. Force is upward. So what would be the direction? And so this would go like this. This electron would go like this. So answer is second one. It's the answer. Right. So here, although the electron is flowed towards right, don't take current is flowing towards right. So always current is opposite to the direction of electron. That's current flow is opposite to the flow of electron. Right. Question, it is said a charged particle having velocity v enters perpendicular to uniform magnetic field of flux density v and follows a circular path of radius r as shown in the figure. The charge of the particle is q, then mass of the particle is. Right. So from this, you can say the force is acting towards the magnetic force is acting towards the center, and velocity is upward. So the what is the direction of magnetic field? So Q, it's Q. Right. That's Q. So what we have to do is just consider circular motion of radius R. Of radius R, velocity is V. V. So apply F equal M towards the center. That's the magnetic field. Magnetic force is equal M. V squared over R. V squared over R that we learned from the general acceleration equal V squared over the radius R. And this is V Q V. V squared over R. This is the magnetic force acting on a charge, EQV. Then V, so we have to find M, right? Yes, mass M is equal V QV divided by PQR divided by QR divided by V was first term. Right. So basically, we learned about we started the magnetic field section today and learned there are two types of magnets: permanent magnets and induced magnets. So induced magnets would right, the induced magnet would show its magnetic properties only if the current flows through the conductor. Right? Whereas permanent magnet, right, the magnetic would magnetic property would be, I mean, we can consider them as permanent, but if it is heated, if the permanent magnet is heated, also magnetic property is lost. Right. So then, by experiments, it was found when current carrying conductor is kept closer to another magnetic field, the current carrying conductor would be thrown away. Then we formulated induced magnetic force. That current carrying conductor is VI L times sin theta. P is the magnetic flux density, and theta is the angle between the conductor and magnetic field. And when the conductor is perpendicular to the direction of the magnetic field, we would have the maximum force, right? Maximum force VIL. Right. So this IL term is called the current element. And then magnetic flux density can be described as the magnetic force acting on a unit current element kept perpendicular to magnetic field. Right? Then the units of magnetic field is Newton divided by amperes per meter, or especially Tesla. When then we talked about the distribution, the magnetic distribution of magnetic flux lines around magnetic permanent magnet and this magnet. So the specialty here is is magnets. That always there comes, we consider magnet, always there is North Pole and South Pole. There's no any magnet having only a North Pole or only a South Pole. Always there's a combination, that this North Pole and South Pole are bounded together. That always there is a North Pole and South Pole in a magnet. Not North Pole separately and South Pole separately. And the magnetic field starts from North Pole and comes towards the South Pole. In the horseshoe magnet, it is like this. And so when a magnet is divided to two segments or couple of segments, you don't get separate North Pole and separate South Pole. You get two magnets each having both North Pole and South Pole. So in a conductor, current can conduct. Finally, how to look at that. When the current is flowing outward from the whiteboard. So we have to point our thumb in the direction of the current. So other four fingers will be directed toward the direction of magnetic field. If it is a circular current can conductor, so we can point the thumb in the direction of the circular current can conduct because it is a circle. So we have to point our four fingers in direction of current, and thumb will be directed toward the magnetic field. This is magnetic field. Right. So here also same. So we have to point our forefinger direction of current, which is clockwise. So the magnetic field is towards left. Right. So we found that. So this force is generated due to the interaction between those magnetic fields. Right. Magnetic force is resulted due to the interaction between these two magnetic fields. Right. So towards left, magnetic field is more stronger because these two magnetic fields are added up. Towards right, magnetic field will be somewhat lower because they are cancelled out. And so due to this variation of the strength of the magnetic field, the conductor will be shifted towards the weaker magnetic field towards right. So, but in order to get the direction of magnetic force, the magnetic force easily can use the Fleming right-hand rule. The right-hand rule. So direct the middle finger, forefinger, and the thumb perpendicular to each other. Right. So when the forefinger is directed toward the magnetic field and the middle finger towards the current, eventually the thumb will be directed toward the magnetic force, induced magnetic force. Then here we formulated, consider charge magnetic field, charge magnetic field, and the magnetic field induced of this charge. So how it's above expression for the current can conduct VIQ. So we can just manipulate this previous expression bit, and get an expression for the current for charge traveling in a magnetic field with velocity v and angle theta to the magnetic field. Having a charge is sine theta, like the direction of the and the magnetic field are perpendicular. We have VQV, is the maximum magnetic force taken on a charge, right? Moving charge. So here we consider the moving charge on a moving charge traveling on a magnetic field, which is pointed inward. The magnetic field is inward, right, to the whiteboard. So here we can see always the force, the induced force, magnetic force is perpendicular direction of velocity. So if the force is perpendicular direction of velocity, direction of motion, it will be a centrifugal force. Centrifugal force. So due to centrifugal force, what would be the result? Final, you would have a circular path, right? Circular path. This charge would have a circular path of radius r. So that's we discuss today. So later, next session, we will learn about something called Hall effect, right? And so still we could still be right. We have an expression for E, separate expression for the magnetic field density. We'll learn in next session. We learn about that test and so that's all for today session. So thank you.